does something morally wrong, I'm sure you'll be fired. But just because he's stupid, you can't be fired. So, but no, I think there's a reasonable chance I'm going to continue to lay march out in my laboratory anyway. And then about 2 months later, Jim Gordon came into my lecture hall where I was lecturing, said, "Oh, it's working." Well, all the students then dashed out and went to the lab and saw this thing, saw the oscillations, well. It took a while before Robbie and Cush congratulated me on this, but eventually they did. Well, now, there's interaction of different fields. And let me give you a further example. After we had one working, I had a sabbatical over in Europe, and I knew old Bohr, who was a friend of mine, the son of Niels Bohr. I went to visit him. I was walking on the street with Niels Bohr, and he asked me what I was doing. I told him, well, we had this new kind of oscillator. I gave a very, very pure frequency, and this is what it does. He looked at me and said, "Oh, no, that's not possible. No, you misunderstand something. No, that can't be right." I'm sure he was thinking the uncertainty principle. The molecules went through a cavity in a finite time, and the uncertainty principle says, well, you can't define the frequency by a certain amount. Because that's for a single molecule, the uncertainty principle. And see, any engineer knows that once you get feedback, amplification and feedback, sure, you get a very narrow frequency. Obvious in engineering. Well, I had been at Bell Labs, and during World War II, I was required to work on radar. So I learned a lot of electrical engineering at Bell Labs, and that was a big help to me. It was obvious to me, but Niels Bohr, who was a bad physicist, he said, "No, that's impossible, it can't work." I said, "Oh, no, we got it, oh, no. Well, he just wouldn't talk about it anymore, wouldn't let me try to explain it. I said, "Oh, no, you've got to look at that again, something's wrong." Now, John von Neumann had the same reaction. He asked me about it. John von Neumann, of course, a great scientist. He didn't get a Nobel Prize, but he was a great scientist. And he asked me what I was doing. I told him. He said, "Oh, no, that's not possible. You can't get this well-defined frequency that way. No, you'll misunderstand." And I said, "No, it worked." Well, there was a cocktail party. He went off and got another drink. In about 15 minutes, he came back. "Hey, you're right. Tell me more about it." So he woke up to it. And I think he was rather broader than Niels Bohr in terms of his background. He had done a lot of good things. So that's where we were. Now, after the laser came along, suddenly that was an exciting field. Nobody paid any attention to it much. They'd come down and see my laboratory and say, "What are you doing?" You know, "Oh, okay." Nobody else competed. Or any other papers, nobody else tried to do it, and so on, except the Russians. And we weren't in contact with the Russians. The Russians had an independent idea of about something to talk about. And they worked on some. They didn't get one built, but they had the idea. But in the United States, nobody had published, nobody doing anything. They came to my laboratory, it wasn't all that interesting. So they had no competition. After it worked, then a lot of people jumped into the field. After it worked. It was a very popular field. It was very, very popular. In fact, so popular, the Physical Review, very unusual case, the Physical Review had so many papers on lasers. They said, "Well, we just had so many papers on lasers, we don't have room anymore, we're going to make a rule, no more papers on it, we won't publish any more papers on lasers." The result of that was, once the laser came along, and the first one was made by Neyman, he sent it into the Physical Review, they wouldn't publish it, because they had this rule. So he had to get it to Nature. Actually, publication. So anyhow, you see how popular it was. So now, after about 2 or 3 years of later, I said, "Well, look, I want to get on down to short wavelength. That's my primary purpose, to get to short wavelength. In fact, just tested it first with microwave lasers with ammonium. I want to get down to short wavelength, so that's the real purpose. When I get good frequencies down in at least in the infrared. So let me sit down and see just how best to get on down to short wavelengths." And I sat down and looked at it and worked out the equations and how to do it. Hey, it looks like we can get right on down to light waves. Oh boy, right on down to light waves. Well, I knew by then it's going to be a very competitive field, so I didn't talk two parallel mirrors for light going back. I was going to have the laser produced in a cavity where the light would bounce around in all directions. It wouldn't be highly directed. But he suggested two parallel mirrors. Why? Well, he'd been working on fabric parole in the brown rich for spectroscopy. You know, these different fields interact. They suggested two parallel mirrors, which was great. And we wrote up, took it to Bell Labs lawyers, and I told Art, well, I'd rather give the patent to Bell Labs than take it to Bell Labs lawyers and they'll patent it. And so he called me up next week and said, well, the Bell Labs lawyers say, well, light's never been used for communication, so they don't think Bell Labs is interested, and they don't want to talk about patent. They told me, if you want the patent, you just patent it for yourselves. And so I told them, well, just go to Bell Labs, the lawyers don't understand. We shouldn't cheat Bell Labs. You go talk to some more, I'll tell them, sure, it can be used for communication. They called me up again and said, well, lawyers say, well, if you can show how light can be used in this light can be used in communication, then we'll patent it. Bell Labs. Wow. So we did, and the patent was written, optical lasers and communication. Of course, the word laser had been invented by myself and my students at lunch one time. Microwave amplification by stimulated emission of radiation. So in optical waves, and no longer microwave, but we call them optical lasers, so everybody knew what a laser was. Don't have most descriptive, but pretty soon people renamed it laser for light amplification, which was much briefer and nicer. So the Bell Labs lawyers did make a patent, and then we decided, well, I shouldn't start work on it, because working in the lab would take a while, and we'll have a lot of competition, and know who would do it first. So let's just write a theoretical paper, which is what we did. We were very quiet about it. We sent in theoretical paper to be published, and then everybody jumped into the field. Now, the first laser was made by Ted Mayman. Ted Mayman was in the industry of Hughes, and all the first lasers were made in industry. Why? Well, industry become various lasers that hired a lot of students in universities working in this field, so they had a lot of good talent. And of course, industry, once it knows it wants something, it can put a lot of energy and a lot of intensity, which they did. And so the first one was at Hughes, the next one was Ollie DeLong, who's been a student of mine, who built up on that course. He made a continuum laser. Mayman made a pulse laser. And pulses hadn't occurred to me, but Mayman had been working with pulses, and so he could use it. Because you get more intensity. In fact, Art Shallow had even written a paper that, well, Ruby would be nice as a laser, but the reoxidation time too rapid couldn't be done with ordinary light. With a pulse light, you could do it, and Mayman saw that, you see. So we see all the contributions that different scientists make, the different points of view, and the interaction between the different fields. Those are all very, very important in the growth of science. Now, then the next laser was done in General Electric, and one of my students and some other people did it, and then it was just one after another. A lot of them came along. And of course, the field has grown. Wow. I never expected to be quite as big as it is. I knew it was going to be important, very important. But I was speculating in the scientific uses, and I still am. It never occurred to me, for example, medical uses. I can see, of course, burning and welding and cutting and transmission and lighting and pointing and all this. I see a lot of applications, but the medical application never occurred to me at all. And they all have a wide variety. And it never occurred to me we're going to get as much power as people use nowadays. Wow. Power is up to the 10 to 15, 10 to 16 watts. Of course, in short focus. The small lasers, big lasers, one being built now out here. There was a building 100 feet high, and it's enormously big things and an enormous amount of power. And because it can be focused to a point, the power concentration is fantastic. Power concentration is focused, of course, to something the size of the light wave. Now, it's also $5 or $10 billion worth of business every year. So it's very important economically, very important scientifically. about a dozen or more, well, I think that counts up 15 in all, Nobel Prizes have been given, which have been dependent on the laser as a tool, or as an invention of the laser itself, but as a tool primarily, it's been used now for doing new things. It produces, of all things, enormous amount of power, very high temperatures, but also produces the lowest possible temperature and cools things down, way, way down to get the lowest possible temperature. One Nobel Prize in that area, of course. Well, now, what does this tell us? I think, in the first place, we've got to be open-minded. It's natural. We learn a lot of physics and think, oh yes, and this is this, and now I figured it all out. I know all the answers. And, well, we don't necessarily know all the answers or the applications. And we've got to be open-minded about new ideas. And new ideas come along, we've got to encourage people to explore them, even if they seem chancy. Even taking chances is worthwhile, because every once in a while something very important can come through. And this is one of the great things about the university. University, if a professor wants to do something a little crazy, well, he can do it. The universities allow that. They can't control what a professor does. He just has to, in the long run, do something worthwhile and important. But what he's doing now, the university don't control it. As industry, they control it much more. Think, well, you know, we've got to make money. We've got to make something that's going to work and help us. So only those things that they see may be worthwhile will we allow generally to be developed and tried out. But trying out new things and taking chances is a very important part of the development of our science and technology. And we must be open-minded. Sure, you don't want to do something that's not going to work, but don't hesitate to try something that's new that might possibly work. It's interesting to be worthwhile. And we've got to allow that part of our scientists and our friends. I think another very important thing is to remember the importance of interaction between different fields. There's an idea over here, an idea over here, and people in each field may not see the other one, but the joining of the two may be something very important, both in science and technology. So the interaction in different fields, the interaction of people, after we get together, we talk to each other and so on, we write papers, and all these things are enormously important in the development of science and technology. Well, with that, I think it's about time for me to stop, and I wish you all the best, and the best in exploration and finding out new things. Thank you.